Hello. Can any one of you hear me? Hello.
Hello.
Okay, can you hear me?
Yes, I can.
Good, thank you. So we are going to go over chapter 9, which is on correlation and regression. So correlation studies the possible relationship between two variables, X and Y. X is generally considered an independent variable and Y is considered a dependent variable. In some cases, there could be more independent variables, and we call it a multiple correlation. The dependent variable Y is generally called the response or the output variable, and the variable X is generally called the independent or explanatory variable. So we generally want to know, is there a correlation between X and Y? Is this correlation linear? Is it significant? Those are the type of question we may want to study. So if there is a significant correlation between X and Y, we may make a prediction, that is assigning value to X to get some values of Y. To start with, we use what is called a scatter diagram. A scatter diagram is a display of the relationship from a sample that can help us to determine the possible nature, whether it is linear or nonlinear, or whether there is no relation at all between the variables. So this is an example of scattered diagram where we represent the value of X in the horizontal line and the value of Y on the vertical line. The red point that we see here are the point X and Y from this sample. Based on this relation, we can feel like a straight line passing through this point could represent a possible relation between those variables. Later on, we are going to learn how to make a scatter diagram using Excel. And these are some other possible type of scatter diagram. The A is a scatter diagram that is indicate a relation between X and Y, which is kind of parabolic. And in B, we have a really scatter diagram that does not show any form of equation. So when we have a linear relationship between two variables, it could be positive or negative. In case of a positive relation, like the first diagram is a positive relation, as X increases, Y increases. In case of a negative relation, as X increases, Y decreases. Let me give an example. Suppose you want to look at a relationship between the time a student spends studying and his score in a test. You might feel that there is a positive relationship, meaning like the more the student study, the higher his score on the test is going to be. But if you want to check the relationship between the time the student spent playing video game every day and the score in the test, you might feel like there is a negative relationship, meaning that the more time the student spend on playing video game, the lower his score in the test is going to be. So this is a representation of positive and negative relationship. When a relationship is perfectly represented by a line, like in graph C and D, we call it a perfect linear correlation. So you will observe that we will hardly get a perfect linear correlation is a natural occurrence of issues but a correlation is still going to be very, very useful to make predictions. So, sample correlation. The sample correlation coefficient is a number which is used to determine the strength, the sign, and the nature of a relationship. Let's start with a nature. If this R is equal to 0, there is no relationship. If R is different from 0, there is a possible linear relation between the variable. The correlation coefficient is useful for establishing that there is a linear relation between the variables. So R is the sample correlation coefficient. The population correlation coefficient will be denoted by the Greek letter rho. I'm going to write that letter when we are on the whiteboard. So whether it's R or rho, when it is 0, there is no linear correlation. If R is positive, the relation is positive. If R is negative, the relation is negative. If R equals to plus or minus 1, the relation is a perfect correlation. Actually, the closer R is to negative 1 or 1, the stronger, not meaning the significant. I mean here is stronger. As R gets closer to negative 1 or 1, the stronger the relationship. All what we say about R concerns the sample. We are going to study inferences that will enable us to determine if the observation we have from the sample can be generalized to the population. When that happens, we say that there is a significant correlation between the variables. To compute the correlation R, we use this formula. If we have to do it manually, we will find the sum of x, the sum of y, the sum of x squared, the sum of y squared, and then the sum of x times y. Then fit it into this equation. But we are going to be using either the calculator or Excel to get this correlation coefficient. Let's look at this example. We are going to get data from this example. That first, I will use Excel to make a scatter diagram, and then use Excel to compute the correlation coefficient. So sand driven by wind creates large, beautiful dunes in the Great Sand Dunes National Monument, Colorado. Of course, the same natural forces also create large dunes in the Great Sahara and Arabia. Is there a linear correlation between wind velocity and sand drift rate? Let x be a random variable representing wind velocity, and let y be a random variable representing drift rate of sand. A test site at the Great Sand Dunes National Monument gave the following information about x and y. So we are going to enter this information into Excel. Can you use your Excel?
Yes.
Can you both use Excel?
Yeah.
Okay. So I'm going to go to Excel now. As I am on Excel, you may not see the PowerPoint anymore. I'm going to enter the values on Excel, and you can enter it on your own computer as well. Generally enter the independent variable on A and the dependent variable on B. If you reverse it, just remember wherever it is, because as you are using Excel, you will just indicate where your variable is. So we start with 70. So naturally, these variables are in pairs, so we enter them as they are. Do you have your variables on Excel?
Yeah.
Now, as usual, we will go to data and then data analysis. Then we will choose regression. So first we will input the Y range, which we decided to put second here. Y range is B1 to B7. So you could enter it in column A and enter it first. Then the X range is A1 to A7. As usual, we are going to choose where we want the data to be. We are going to come back to this confidence level that is in inferential statistic. I mean, it's when we will try to do inference, we may have to change the confidence level according to what is required. So here, oh, I wanted to make a scatter diagram first, but a scatter diagram is not difficult. You just highlight the values and then so this Excel output is giving us a lot of information, which we are going to come back to. But what I am interested on at this point is the correlation coefficient, R. So at this point, what we need is only the correlation coefficient. As we move on, we are going to come back to it, to the data. Are you able to get this?
Yes. Yep.
Okay. So if we were to make a scatter diagram like we did the graph in chapter 2, highlight the graph, choose insert, and this is the scatter diagram. You just choose this, and you have the scatter diagram. If it is on a test or if it is on a work that somebody asks you to do, you then copy it and paste it on Word. I can place it here. So this scatter diagram indicates that there is a possible linear relationship, that is a straight line can pass through this point, as we can see from the value of R. So going back, let's go back to the PowerPoint. So you use Excel, you will not always have time to use the formula. If you were to use your calculator, you can also use it if you like. Maybe at the point we are going to use calculator so that you know how to use calculator to do this. It is actually in the PowerPoint. So after computing the correlation coefficient, we are interested in determining the equation of the line that can best represent the relationship between X and Y. Could a line, what is the line of best fit? The line of best fit is the line that can best describe the relationship between the variable. It is also the line that is the closest to all the points of the scatter diagram. So we call it the least square line. And here we have a description of how to obtain it. Let me go to the whiteboard to explain. So suppose we have data represented as a scatter diagram like this. So we make a straight line that passes through the point. And we want to determine which line is the closest. I can make another one. So what I want to show you is how do we find the distance between a point and the line. So we draw a line from the point perpendicular to the line. We find the distance from each point to that line. So that distance is generally d equals to square root for the first distance of x1 square minus x2 square. I'm sorry, x1 minus x. Let me change this. The distance, if the line here is y equals to x, maybe ax plus b, we are going to use something like that. Let me write it this way. Y equals to a plus bx is the equation in your book. So we are going to find the distance between each point. The first point, d1, is x1 minus x square. You don't need to write this plus x2 or y1 y1 minus y square. The reason why I'm doing this, because you will see that d1 square will be x1 minus x square y1 minus y square. So then we will add all these distances, and the values x1 and y1 are the values from the sample. And we are going to use it with calculus to determine the point where we will achieve the minimum values of the distances. In doing so, we will find that that minimum value is achieved when b equals to this formula, n sum of xy minus sum of x times sum of y over n sum of x square minus sum of x all square. And a equals to y bar minus bx bar. Y bar is the mean of the y values, x bar is the mean of the x values. You will as well not need to be doing these computations because you will use either your calculator or Excel to get the value of a and y and b. So before we get to this example, I want us to go back to Excel. And in Excel here, I want you to identify two more values. What we call here the intercept is the value A. Is called the intercept. This value A is called the intercept. This value B is the coefficient of the X variable. The coefficient of the X variables. Those are the values A and B that we just described, which defines the regression line. We are going to look at another example, and I will come back to Excel again. In this example, we start with the Denali National Park in Alaska. In this park, the wolf population is dependent on a large, strong caribou population. In this wild setting, caribou are found in very large herds. The well-being of an entire caribou herd is not threatened by wolves. In fact, it is thought that wolves keep caribou herds strong by helping prevent overpopulation. Can the caribou population be used to predict the size of the wolf population? That is our question. Let X be a random variable that represents the full caribou population in the park. A random sample of recent years gave the following information, where Y represents the wolf population. So we have this, and we are going to use Excel to determine the correlation coefficient between the caribou and the wolf population, and also to determine the regression line passing through the X and Y values. Let's go back to Excel. And the X values here are 30, 34, 27, 25, 17, 23, 20. The Y values, 66, 79, 70, 60, 48. So then next we go to data analysis, regression. It happened we still have A12, essentially the same thing, and we can click OK. So what do you think is the correlation coefficient here? Can any of you tell me what the correlation coefficient is?
Is that R?
Yes. It is called here multiple R because it is also used for multiple correlation. So what is the value?
0.915.
That is the correlation coefficient. Now, what is the intercept for the regression line?
Is that going to be 22.360?
Yes, 22.36. And then the slope is the number that is in front of X. That is why we call it the coefficient of the X variable. It is also called the slope. And what is that slope?
Is that 1.5999?
Yes, we can round it up to 1.6. So those information are very useful in your quizzes, in your homework, in your test. Sometimes I will just ask, what is the correlation coefficient? What is the intercept? What is the regression line equation? What is the equation of the regression line? Equation of the regression line here will be 22.36 plus 1.59 or 1.6x. So we are going to go back to the PowerPoint. So in the PowerPoint, it is explained how to compute this manually, but you should use Excel. So we will need the mean of the X values and the mean of the Y value because it helps us to find A. once we know B from this formula. You don't need to do it, but I just want you to see. So this is the B, the slope, 1.6, if you could remember what we got from Excel. And A is the slope, 22.35. So that means that the equation of the regression line is 22.35 plus 1.60x. In our next example, we are going to use the calculator because I want you to be able to use both the calculator and Excel. So now, what is the use of the regression line? The regression line is useful in finding an estimate of the predicted variable. Think about the values we had here. We have the equation. Let me keep that equation. This is the regression line equation. Y hat equals to 22.35 plus 1.60. If there is a significant correlation between the variable, we, given the x values, can predict a y value. As I told you about the example of the time you spent studying and your score in the test, if x is the time you spent studying, I can determine using the regression line the score of the test, the score of the test you are going to have based on the time you spent studying, if it is already established that there is a significant correlation between the two variables. For example, here, let's take an example of an x value from the data we have. So recorded information from this pack told us that for a population of 3,400 Caribou population, we had 79 wolves. So this is values observed. These are observed values from the data. We are going to get a regression line that can help us find a predicted value for this, for 3,400 Caribou population. So using the equation that we just computed, let's see what we will get in case we did not have those values and we had this equation. What value are we going to get for the wolf population? For x equals to 34, we will replace 34 here and get an estimated 76.75. Do you see here that this value is not exactly what we got from the sample? Do you remember what we got from the sample? For a Caribou population of 3,400, what was the wolf population? Caribou population of 34, let's just say Caribou population of 34. What did we get for the wolf population?
Was that 79?
79. So 79 is the actual record of data collected. 76.5 is the prediction from the regression line. We can see that in the absence of the actual data, this number is kind of close to what we would have had if we went on to count the wolf population. But it's not the exact value. This value is the point estimate of the wolf population, the point estimate for the wolf population, which we can use to find even a confidence interval, for example. So next is that the difference between this estimate and the actual value, which was 79, is called the residual. is called the residual. The residual is the difference between, I don't know where that word is here. Anyway, the residual is the difference between y and y hat. Y hat is the predicted value based on the regression line. Y is the actual value which we want to estimate using the regression line. Coefficient of determination. So the coefficient of determination and non-determination are useful information that could help us to determine some values in a regression. First, remember that when we were finding the standard deviation or the variance, we first find the difference between each value and the mean, the sample mean. That difference is called the total variation. The difference between the estimated value using the regression line and the sample mean is called the explained variation. And the difference between the actual y value and the predicted value y hat is called the residual. These information are useful to determine what we will call the coefficient of determination. So the total variation here, when we square the deviations from the mean and add it up, then the deviation from the mean of the predicted value and square it, and the residual, the square of the residual, we get first the total variation, then the explained variation, and the unexplained variation. All those I'm just explaining, we will go back to Excel to see the numbers. R square is explained variation divided by total variation. And that is what we are calling the coefficient of determination. It is just the square of the correlation coefficient. So R square, the coefficient of determination, is the proportion of variation of the dependent variable that can be explained by the regression line. The coefficient of determination is the proportion of variation of the dependent variable that can be explained by the regression line. On the other side, the coefficient of non-determination, which is 1 minus R squared, is the proportion of variation of the dependent variable that cannot be explained by the regression line. So let me go back to Excel and we will see where those numbers are. So this is R, the correlation coefficient. This is R squared, the coefficient of determination. So if I had asked you what proportion of variation of the world population can be explained by the regression line and the independent variable, you will just say, let's say 84% or 83.7%. And what proportion is not explained? If you say 84%, then 16% cannot be explained by the regression. It could be what we call a lurking variable. So gradually, I am giving you information about each of the values. This one is not very useful for now. We are going to discuss this next, the standard error of estimate. The standard error of estimate. Now let's go back to the PowerPoint and discuss inferences. So what we have discussed so far are based on the sample. Inferences consisting of generalizing information from the sample to the population. So for example, a statistic in correlation can be the correlation sample correlation coefficient R, and the corresponding parameter is letter rho, which is like P here. Then as we express the sample regression line as a plus bx. A is the intercept, and for the population is alpha. B, the slope in the sample for the population is beta. So we generally make inferences about beta and rho. Those are important inferences we could make. And we use the same test. As you saw in chapter 8, we will use the same test value and the same p-value to test the significance of the correlation. So in testing the correlation, the null hypothesis is generally rho equals to 0, meaning there is no correlation. And the alternative hypothesis is about one of these three. Rho is positive, rho is negative, rho is different from 0. When you are using Excel, Excel is only testing for rho different from 0. If you are using your calculator, you will have the option to test whether it's positive or negative. Also, I want to mention that Excel is always give you the absolute value of R. Your calculator gives you the actual value. To know whether the correlation is negative or positive, you should look at the slope. The slope, the sign of the slope on Excel is what tells us whether the correlation is positive or negative. So the test value is this: T times R times square root of n minus 2 over 1 minus R squared. And we use the T distribution with degree of freedom n minus 2. So if the p-value is less than alpha, you reject the null hypothesis and conclude that there is a significant correlation. If the p-value is greater than alpha, you do not reject the null hypothesis, which was rho equals to 0, and conclude that there is not a significant correlation between the variables. So before we look at another example, I want us to go back to the results we have had from Excel. So let's look at this result. This is the test value, which is called test statistic. As I said, we are going to be testing for the slope, the test of the slope, especially for a one variable for a simple correlation. The test for a slope is enough to test for the correlation. If you look very well, what number am I indicating here? The p-value for x variable, what is it? Can any of you tell me what number is indicated here? The p-value for the x variable?
Is that going to be 0.003861?
Yes, that is the p-value, and the test value is 5.07. So if we had a level of significance alpha equal to 0.05, then this p-value is less than alpha, and we will say that there is a significant correlation between the caribou population and the wolf population based on the p-value. So if you are asked to find the t-value for a test of correlation, just choose this t with x variable. T stat for x variable. The standard error of estimate is the square root of the sum of the square of the residuals divided by n minus 2. It is generally useful in the formula. This is the formula to get it, but as I told you, we can get it from Excel, standard error on Excel. It is generally useful. Let's look at this example. June and Jim are partners in the chemistry lab. Their assignment is to determine how much copper sulfate will dissolve in water at each of the following degrees. So, can you grab your calculator?
Yep, I've got mine.
Do you have your calculator with you?
Yep.
Okay, so let's go to start. And we will enter the values in L1 and L2. X in L1, Y in L2. Do you have your data in the calculator?
Yes, all entered now. All set.
Okay, so we go back to start and test, and we scroll down to linear regression test. Linear regression t-test is letter F. So by default, your data is in L1 and L2. If you are entering it somewhere else, you will have to change it here. So mine is on L1 and L2. And we can choose if we want to test for two-tailed test or one-tailed test. Let's choose two-tailed test. Let me see what the Excel's here, what we want to test here. No, it's not important. They didn't ask us to do any test. So let's just choose any. We will choose the two-tailed so that it matches with what we have on Excel. And then you calculate. So what is the test value here?
11.42.
11.42. What is the p-value?
Negative 0.00. Oh no, it would just be 0.00008.
Wow. Yeah, that's right. I was expecting you to tell me 8.98. Okay, now you know. So it's 0 point, you make 40 because it's -5 and then 89. So it is very, very small, indicating a very strong, significant correlation. You just need to say there is a significant correlation. So what is the slope of the regression line? I'm sorry, let's start with intercept. What is the intercept of the regression line? Y-intercept, A.
Oh, is that going to be 10.14?
10.14. And what is the slope?
Is that going to be 0.50?
0.50. And then the standard error?
2.34.
2.34. Now, the coefficient of determination?
That's 0.96.
R square, yes. R square is the coefficient of determination. On Excel, you get R before R square. And the correlation coefficient?
Oh, okay. So that's 0.981.
Yes.
Okay.
So those are the information that you may be question about in your quiz or on the test or exam. So you need to know when you are using your calculator or when you are using Excel, what to use. There is another type of question that could come up. Estimate a value of y given a value of x. I have already told you about that when we replace 34 in the equation. You will replace the x value in the equation and you will get a number. Now, next thing we want, I just wanted you to know how to use calculator as well. So this is the equation, the regression line, 10.14 plus 0.51. And there is a prediction here for x equals to 15 that gave 17.8. The standard error, you saw it there, S equals to 2.35. This standard error is generally useful in finding the confidence interval for beta and for y. We start with the confidence interval for y, which I don't generally ask you because the calculator, all calculators are not yet doing it. Some calculators are able to do it, but some are not. Let me check if your calculator could do it now that you are here. Can you go back to start and test?
Yep.
You see linear regression t-test?
Yes.
Now you have linear regression t-interval.
Yes.
Okay, you have L1, L2. Let's just leave it at 0.95 and calculate.
Ooh, for where should the 0.95 be?
Pardon?
I have an X list, a Y list, frequency, sea level, I have 0.055.
No, just make it 0.95, for example. We usually do 95, 90, 99.
Okay. And should I put anything for regular EQ?
No, don't put anything.
Okay. Okay, got it. Okay, so is that going to be from 0.39 to 0.62?
Yes. This is the confidence interval for beta. So I have skipped the confidence interval for y because your calculator does not have a formula for it. Excel does not have a formula for it, but this is the formula. But I don't ask you that question because you will need to use this formula, and we have not been using formula. So for this single one, I skip it. I don't ask you question about confidence interval for y, but I ask you questions about confidence interval for beta, inferences about the slope, and that is what you just got. So let's do confidence interval. The confidence interval you have on your calculator is about the slope. You got it? So I just want us, well, we can skip this as we are already about 50 minutes and I want us to go to 9.4. What I'm going to do is go back to Excel and show you how to read it from Excel. What we did on Excel, you remember, do you have your Excel?
Yes.
So you have this, the confidence interval is here. For Excel, the confidence interval is here. I am trying to make it visible. So lower 95, upper 95. Do you see that?
Yes.
Okay, if the confidence level was 95%, then that's not what we did on the calculator. So it's not the same. I mean, you will not see the same values. So then the confidence interval for beta, for this wharf, caribou and wharf population, the confidence interval for beta is 0.79 to 2.41. That is the 95% confidence interval. So if I had asked you for a 99% confidence interval, this is what you will do. You see here, are you seeing what I've just done?
I'm sorry, I missed how you got to that box.
I got here just by going to data analysis. You see data analysis on your Excel?
Yes, okay, got there. Sorry about that.
No problem. Now you go to regression. It's just exactly what we did before, but at that time, I just mentioned to you that if the confidence level is different, you check here and change it to the new confidence, like 99.
Gotcha.
Then it is going to change what we have here. So you see here is 90, the second one is 99, lower 99, upper 99. Do you see what I'm talking about?
For some reason, something funky happened on mine. Sorry.
No, tell me what happened. When you click OK, there was a notice that popped on.
Yes.
You were supposed to just click OK.
Okay.
Just do it and click OK there.
There we go. Thank you.
You're welcome. Sometimes it's just good to say.
Yeah.
So what happened is that you already indicated that you want your outcome to be on the same place where something is already. So they're asking you, should we replace it? So you say, okay, because it will be the same information.
Gotcha.
Mm-hmm. So now what you will observe here that before everywhere was 95. Now the last two are 99 because we changed it to 99. Do you see what I'm talking about?
Yes. Yep.
Do you have 99 on your calculator? I'm sorry, on your Excel?
Yes, I do.
Okay. So the confidence interval for the slope for 95% is this default. It is always there. So the confidence interval for the slope at 95% is 0.79 to 2.41. At 99% is 0.32 or 33 to 0.28. So if I do not ask you for 95%, remember with your calculator, you change it to 0.95. So in calculator, you can always just put the actual confidence interval. But the advantage of Excel is that you do one work. If you do all the right clicking, it gives you everything that you need. And each time you have a question, you just read it from the Excel.
Gotcha.
The calculator, the test, and the interval are two different keys.
That makes sense. Gotcha.
Okay. So we were here and we have, we are not doing this one, but we are done. So do you have time for us to go over the project?
Yeah, that would be great. Thank you.
Okay, good. Yeah, so I will just do the project here. I will just explain the project now. And for those who are, I mean, I will just be sending people to come to the project, I mean, to the PowerPoint or to the video. So project. So about the project, what we did so far is a simple correlation. In a simple correlation, you have one dependent variable and one independent variable. Sometimes you have more than one independent variable. Let's say, for example, we are trying to look at to estimate the test score of a student for a specific exam. And we know that there is a correlation between the time the student spends studying and the score as the dependent variable. But those are not the only, that's not the only variable that can determine the student's score. You might want to measure the level of anxiety of the students in taking the test. You might want to take into account the time the student spends studying. You might want to also take into the account the time the student spent watching TV. Now you are getting into about 3 independent variable or 4 with the same dependent variable, which is his score in the test. So with this example, let me get out of, we are going to practically do one. So we are going to have the student score is Y, and we are going to say the slope is A plus B1, and X1 is the time spent studying, X1, plus B2, anxiety level, maybe plus B3, maybe time of the test. Some people test better in the morning, some people test better in the afternoon, and so on. Or we could say X3 is the amount of time the student spends sleeping. So this gives you a correlation with more than one independent variable, and we call it a multiple correlation. So the procedure remains the same. We are going to learn how to enter data into Excel. You can also use your calculator for that, but I encourage you to use Excel because Excel is more professional. You can enter your data into Excel. Here, the test of significance is the F-test. I'm going to show you where that F-test is. You can also use it for single value. Essentially, test value help us to get the p-value. And the p-value, we use the same rule. If less than alpha, the correlation is significant. Otherwise, the correlation is not significant. Something more to add into multiple correlation is that there might be a significant correlation between one and more than one variable, like I said. And then there is a variable in it that does not really have an effect on the correlation. So in addition to checking the correlation coefficient in general, the significance of the correlation in general, we can also test the significance of each of the variable. Okay, when we do an example, you will understand better. So for your project, you are going to collect at least 3 variables from at least 6 individuals. This is just an example. Let's say that you want to determine if amount of sleeping time, length of study, level of anxiety are all correlated to the score in the test. That means you have 4 variables. One is the dependent variable, which is the score in the test, and the other 3 are the independent variable, which are time you spend study, time you spend sleeping, and level of anxiety. That means you have 4 variables. In simple correlation, we deal with two variables. For it to be a multiple correlation, there should be at least three variables in which one is the dependent variable and the others are the independent variable. So you collect your data and list it on your project. I'm going to see if it is three columns. If it is four columns. You are going to tell me which variable is the independent variable, is the dependent variable, and which are the independent variables. Identify the dependent variable and the independent variable. In the example that I gave you, you will say the score in the test is the dependent variable. The independent variable are length of sleep, length of study, level of anxiety. Then you will find a regression line. I will show you how to find that on Excel. It's similar to what we did for simple correlation. Test the significance. In testing the significance, you just need to identify the test value. Actually, the H0 is rho equals to 0. H1 is rho is different from 0. Then your test value is F. And the p-value, if p is less than alpha, there is a significant correlation. Otherwise, there is not a significant correlation. Then now, this is test the significance of the correlation between the variables. 5, choose enough independent variable to make a prediction of the dependent variable associated with them. What this means is you had, let's say in our example, 4 variables. Test score is the dependent variable. That is what you want to predict. Then you have, you will choose maybe one of your data from any of the individuals, or you can make it up. You want a length of time of sleep, maybe X equals to 6 hours. Length of time of study, maybe X equals to 2 hours. And level of anxiety, which you might say is maybe 3 or 4, whatever is the level of anxiety. Then you fit it in that equation, which was y equal to maybe 3 plus 2x1 minus 3x2 plus 2x3. You replace x1, x2, x3 by the values that you just assigned. And that is the answer to 5. Now, what is the coefficient of multiple determination and non-determination? This is just r squared and 1 minus r squared. So in some time, okay, let's go to 9.4. We will do an example which will reflect what is expected for you. So what I have just explained about multiple correlation is the content of 9.4. So as I just say, in a multiple correlation, you will have to check the relationship between a dependent variable y, for example, sugar content here. For example, the sugar content y of golden delicious apples taken from an apple could be predicted from the number of days in growing season, x1, the soil quality, x2, the amount of available water, x3. So that is an example of correlation, and you may have a regression line of this form. So in this example, we want to study the relationship between the antelope, a beautiful and graceful animal that lives on the high plains in the western United States. Thunder Basin National Grasslands in Wyoming is home to hundreds of antelopes. The Bureau of Land Management has been studying the Thunder Basin antelope population for the past 8 years. So we are going to say the spring found count is the dependent variable y. The size of adult antelope in 100 is x1. The annual precipitation, x2. And the winter severity, we will make it from 1 to 5. You have seen that sometimes in some survey. So we want to establish a correlation between the spring found count and the size of adult antelope, annual precipitation, and winter severity. So these are the values. Do you have time so that we practice it on Excel?
Yes, that would be great. Thank you.
Okay, let's do that. That will help those who are not here. So thank you for being available for that. Okay, so I'm going to go back to Excel. As I did before, I am not sure you are seeing my PowerPoint, so I am going to write first. Unlike the simple correlation where I start with X, then Y, for multiple correlation, I will put Y first, then list all the independent variables. I could still do all the independent variable, then I put the Y at the end. So it doesn't matter. You just need to know where they are, but your independent variable has to be together. Do you understand what I mean?
Yes.
Okay, let's put the dependent variable 2.9, 2.4, 2, 2.3, 3.2, 1.9. So these are the dependent variables. Sometimes it's good to start with Y, but if you remember, you will know that the first column is the dependent variable. Now we enter the independent variable. So you are going to think about what it's going to be your dependent and what are your independent variables, and collect data as together. Let me know when you are done.
All set.
Okay. So now we go to data, then data analysis. Just the same thing, and regression. So our dependent variable is column A, A1 to A8. Now for the independent variable, we are going to highlight them together. That is B1 to D3, to D8, I'm sorry. B1 to D, have you seen how I did?
Yes.
So you highlight all of them together. Now we are going to change where the outcome should be. I can put it now on F. And we are good. Suppose now we want to answer questions for our project. The first question was collect data. Collecting data will consist of listing all this data. You are going to give me a table of your dependent and independent variable. The second question was identify the dependent and the independent variable, which we did here. The dependent variable is it is on so this is what you want to give me. The dependent variable is y equal to spring found count. I mean, based on your own project. X1, the independent variable are size of adult antelope. X2, annual precipitation. X3, winter severity. I just want to be sure that you know what you are doing. And then the third question was, what is the regression line? Here, the regression line is the intercept is minus 5.92. Do you see it here?
Yes.
So that stand alone, y equal to minus 5.92 plus 0.34 x1 plus 0.40 x2 plus 0.26 x3. Do you see where I'm getting those numbers?
Yes.
Each of these variables, you write the number in front of it, x1, x2, x3, to make the regression line y hat equals to minus 5.92 plus 0.33 or 0.34 x1 plus 0.4 x2 plus 0.26 x3. That is the regression line. Next, you will be asked to make a prediction, I guess. What is the regression line? Test the significance of the correlation, very important. Test the significance of the correlation. Look at it here. This number is the test value. You could also use it for simple correlation. It will be right, but I did not want to say that so that you don't get confused, because what you will get from your calculator is not going to be the same as what you get here. So F can be used even for simple correlation, but we use it more for multiple correlation. So F, the test value is 50.52 and the p-value is 0.001. That's the p-value. You know to test the significance of the correlation, or it's the p-value that is important, but you need to state F value, the F value, so that I know that you know is the F test which is used. You write rho H0, rho equals to 0. H1, rho is different from 0. Test value F equal to 50.52. P-value equal to 0.01. Compare it to alpha, make the decision either to reject or not to reject, and then state whether there is a significant correlation. Almost half of the project. Test the significance. This has a lot of weight. This is generally 3 points out of the 10. I mean, this is generally like 1.5 point out of the 5. I think this project is 5 points. This, and then choose enough independent variable to make your prediction. I'm going to go back to the PowerPoint, which you could use from Excel too. So the least squares regression is given using the coefficient expressed in the last 4 rows of the Excel output. So this is the regression line. It was supposed to be y hat, but sometimes I didn't type it correctly. To type that hat is not always easy. So, but this is the regression line. I want to place a hat here. So this is a regression line, and we are going to assign values to x1, x2, x3. Generally, you can pick one of the set of your data, but align them together. And we put it into the equation to get y equals to 2.33. That's the answer to that question of make a prediction, assign values and make a prediction. So what is the coefficient of multiple determination and non-determination? Here is r squared and 1 minus r squared. So the coefficient of determination is 97% or 0.97. And the coefficient of non-determination is 3% or 0.03. So that is the project. So I am recording this. You can always go back to Canvas to see what we have done tonight. To test the significance of, I didn't ask you this on the project, but to test the significance of each coefficient, let me show you what I meant by that. I mentioned it, but I didn't, it's not a question of the project anyway. You look at this p-value, you see that you can check from each of these p-value, you see the p-value for each variable.
Yeah.
So you can see that the first two p-value are more significant than the third one, but all are less than 0.05, so they are all significant. In some studies, you might see that one of the variable is not significant. Then you remove that one and you continue your study. Okay, Andy, any other question?
No, I think that's great. Thank you so much.
You are welcome. And if you have any question, send me an email. We are almost to the end. One more chapter and we are done.
Yeah, crazy.
Yeah.
Thank you so much.
You're
Thank
welcome.
you.
Okay, you guys, Alexis, have a nice evening.
Thank you, you too.
You too. Bye.
Bye.
It's kind of crazy how only two of us come to these